Super excited to be here again at MLOps. Always great to see and learn from what folks are doing in the community. And hopefully I can share a little bit of what I've been looking into and learning about and building myself over the past year. Today, as Mark said, I will hopefully provide a somewhat high level, but hopefully concrete enough practical field guide to optimizing small language models, SLMs, for domain-specific agents. So I want to start here. Last month, NVIDIA published a position paper stating that SLMs are the future of agentic AI. In this paper, they highlight a few key reasons why they think this is the case, some counter-arguments we won't get into, and some barriers for adopting SLMs, which we will get into. And really, the one motivating claim of this paper is that while language models are often thought of as these general purpose tools that can perform open-ended dialogue, scientific research, therapy, and a lot of other stuff, not unlike the movie Her, in the context of agents, when you actually go and build them, they're actually used to carry out a small number of repetitive tasks with little variation. These tasks can't be done with deterministic software, but can be done with language models. But nonetheless, they are not as grandiose as being general purpose tasks. All right, so they claim that SLMs are a little bit more like the Rick and Morty butter robot whose only purpose in life is to pass the butter. Like that's sort of more the neighborhood of tasks that LLMs are being used for today in agents. In some cases, right? Some domains. The problem is that even if we take this prescription to be true, this premise to be true, the issue is that once you start using SLMs, they need a lot of love. They need a lot of fine-tuning, prompt optimization. You need to get the data sets and eval data sets for that. And once you start diving into this, not that LLMs are potentially orders of magnitude more complex, but most AI ML teams won't really have that much of the resources to deal with LLMs in the same way as they can with SLMs. And once you get into this world of SLMs, you're back in the world of machine learning, pre-ChatGPT hype, right? You're back in the world of worrying about model deployments and monitoring and maintenance and fine-tuning and all the tooling infrastructure around that and what that entails. And to make a little chemistry analogy, just like how a catalyst can lower the activation energy of getting a reaction going, using the right tools and practices can drastically reduce the cost and effort you need to spend to enjoy the benefits of using LLMs in production. So the main thrust of my talk is that by using resource-aware AI-native orchestration, we'll define that later, to build and deploy SLMs, you can scale up experimentation, optimize train and test time speed, stop worrying about writing AI and MLOps glue code so you can dramatically lower costs without sacrificing too much accuracy, and in even some cases, get better performance out of these models and in a domain-specific agent application. So before we go in, I just want to be very clear here. This talk is about LLMs versus SLMs, not about SaaS-hosted versus self-hosted, which can be easily conflated. So as you can see here on the left-hand side, you have a SaaS-hosted. You can use a SaaS-hosted LLM through services like OpenAI and Anthropic, and indeed many do. You could also use SLMs through similar services like LibreChat and the now defunct Hugging Chat. This is different from LLMs versus SLMs. And in this talk, I'm focusing mainly on ML and AI teams who, for whatever reason, own their own the entire technology stack, including self-hosting language models that power their agents. This could be you. This could be because you're in a highly regulated industry like finance, or you have strict data policies, like you're in the biotech or health industry, health sciences industry. And I have personal experience through my work at Union and Flight that these are very real concerns. Many of our customers don't use the hosted LLMs and choose to build and self-host on their own infrastructure. So this talk is also geared towards those kinds of teams who need operational and cost efficiency without sacrificing performance. And so for the rest of this talk, I'm going to unpack the SLMs or the future paper just very briefly. Don't want to linger on it too much. Then walk through a journey from LLMs to SLMs, kind of a pain-driven development story. Then I'll get into these strategies that we've learned about to adopting SLMs and use a SQL agent case study to kind of motivate and build on the strategy. And throughout the outlining of the strategy, I'll also kind of talk about how resource-aware AI orchestration can get you fully operational with LLMs. What are the different practices at a high level? Don't have too much time to dig into super technical details. Obviously, we can ask and can reach out to me later. So first, let's get on the same page. What are SLMs in the first place? So I'm going to go off the NVIDIA paper definition, which I think is pretty good. SLM is a language model that can fit into a common consumer electronic device and perform inference with latency sufficiently low to be practical when serving the agentic requests of one user. And so obviously this is time dependent. 10 years from now, we'll have much more powerful common consumer electronic devices. It's a pretty good working definition. And just to be complete here, the complement of the set, LLMs are basically language models that are not SLMs. And so the paper, they outline why they think this is the case, why SLMs are the future. And they outline 3 points. The first one is will be kind of the focus for today. But the 3 points here are that they are already today sufficiently powerful to use in agents. They are more operationally suitable for agents, meaning they're easier to tune and customize and deploy. And the thing maybe enterprises are interested in is that they are more economical in agentic systems. So to give you a sense of that economical point, if you just look at the Qwen 3 family of models, you have the largest one to 35 billion parameters, and one of the smaller ones, the 4 billion parameter model. If you look at their inference time memory requirements, you'll roughly need 470 gigs for the large model and 8 gigs for the small model, plus some padding for when you actually do inference. So you have the input tensors and the activations and stuff. And this translates to, if we just look at some cloud instances from AWS and GCP, roughly a 100x savings if you were to just luck out. This is the most optimistic kind of savings you can have on this, where you just luck out and your SLM just magically works on your application, which is not the case. So this is in reality, you will incur less savings because there is a cost to now maintaining and deploying and fine-tuning these small language models because they don't immediately work well out of the box. Some barriers to adopting SLMs. Again, the first one is what we'll focus on in this talk, is that there is a large amount of upfront investment, and I would extend this to ongoing maintenance investment involved with centralizing and managing your own language model inference infrastructure. And the other 2 are a little less relevant to this talk, but I'll speak to them anyway. So the second one is about kind of unfair use of generalist benchmarks to compare these SLMs to LLMs. Obviously, LLMs will do better in a benchmark that is composed of a wide variety of different tasks. There are some references that you can poke me about later, but if you actually look at benchmarks that are tool use, for example, or very much more specific to what people use agents for, LLMs and agents for, they'll often do as well as LLMs. The third one is lack of popular awareness, which hopefully this talk will somewhat address by just speaking to SLMs as a viable production technology. So now I'm going to go through a pain-driven development story of how do you get to an SLM. And this is something we've seen through our own Union's own user research. Folks that we've talked to who are building these kinds of systems. And you start off, we're going to talk through time of the operational cost and complexity of your agent application as it matures, right? So when you're starting, you're an AI engineer, you're building a POC, you're the only user, and you're asking the question, does my application work at all if I use a state-of-the-art LLM? And so you get a demo, looks reasonable, and you do an alpha release. You kind of release this internally to some of your teammates, let's say, and you're thinking it works okay, but now I need to start optimizing my prompts to improve performance. I need an eval data set. I need to just make sure that this agent doesn't regress and the performance doesn't degrade. And then from there, you may expand this to a beta release where you share this with some internal or some small set of customers, right? And you're thinking now we have a few more users, you get some monitoring in place to make sure the system upholds your SLAs. Maybe you have a latency requirement for having when your agent responds to a question or a request. And the last stage is kind of when you reach the dumpster fire stage of this, where you release this generally, you're optimistic, and you 100x your user base if you are so lucky. And you say like, oh shoot, we have a bunch more users, our cloud costs are skyrocketing, we have latency spikes all over the place. Now we need to refactor our code to be more resilient. The retries are causing our application to death spiral, and performance is degrading over time. So this is something, a very stylized story, obviously, to exaggerate it, but this is something we've seen in reality with folks that we've talked to. So the rest of this talk, I'll talk about the strategy for adopting SLMs. This is kind of like a framework for just thinking about, even if you haven't reached that dumpster fire stage of when costs are spiraling out of control, this is a way for you to reason about how your journey of how you would get to a small language model. And I guess I want to emphasize that not everyone will reach this phase. In some cases, some use cases, an LLM will just work. So we're going to build, in theory, a SQL agent using Flight 2.0. I'll talk a little bit about Flight 2 a little bit later. But we're going to first identify key leverage points in the agent workflow to see where you can have the most bang for your buck. We'll talk about maintaining performance. So when you're swapping out LLMs for SLMs, you're going to want to maintain the performance, to have it be on parity or ideally better, or maybe you have some margin of acceptable performance degradation. But you want a sense of how well your system is doing overall anyway, right? This is just best practice, period. And you want to optimize experimentation speed, right? So this is not the speed of inference time for your agent, but this is when you're twiddling all the different configurations in your system and finding the best settings and configuration for your system as a whole. And part of that does include what model are you actually using. Then we're going to talk about managing costs with heterogeneous compute and optimizing inference speed to get the most performance out of your system so that your user isn't waiting 30 seconds for their first response. So we're going to ground our strategy walkthrough on this kind of SQL agent, where you're kind of doing a lot of hand waving here, but basically get a user query, like say, what is our conversion rate for our customers for this particular feature over the last 3 months, right? And you want the SQL agent to run the query, analyze the results, etc. So oftentimes you'll have this kind of, I'll call agent orchestrator language model that is doing the most complex job. It's looking at the query, it's figuring out what tools and downstream LLM calls it needs to make to fulfill the user query. So oftentimes this is the last thing you'd want to change. But on the right-hand side, you have 2 tools here, a SQL tool call for getting the table metadata and actually running a SQL query. And then you have a bunch of other downstream LLM calls here for converting the user query into some SQL CLI commands for the agent to get more context on what tables are available, et cetera. All the way down to creating the query, refining it, running it, verifying the answer, finalizing the answer. So this is the general shape of these kinds of agents. There are many different design patterns, so we won't get into that. Building a SQL agent on flight 2 will just help us reason about some pseudocode that we're going to see and make concrete some of the practices that are useful when building these things. And just for those of you who don't know, flight 2 is a durable, fully dynamic, resource-aware AI orchestrator that solves several problems. The problem of having to learn a DSL, flight 2 is just Python, plain Python. It solved the problem of limiting yourself to static DAGs. These are fully flexible, fully dynamic workflows. Helps you with brittle pipelines so that you're tolerant to failures, intermittent network failures and stuff that you can just recover from and not have to go back to the very beginning of your agent call. Helps with debugging any particular stage in your agent pipeline. It can help with massive fan-outs. So it's hard to parallelize. Let's say the agent has to do some research and it has to fan out and do a bunch of web calls, right? So it helps with that. And it helps with the problem of the fact that best practices are hard to implement. And so we've baked into the platform and the SDK many of the best software engineering practices that we've seen when it comes to ML and AI. So in the end, what you get is a very fast AI ML native orchestrator that can be seen as an agent runtime. So you can see in this GIF here, the UI, and it's a kind of silly toy agent that gets a plan and executes the plan to make a peanut butter jelly sandwich, not unlike the butter robot. But this is one of our kind of toy example demos. So the first point I want to make is we'll kind of go through some pseudocode. You don't have to understand all of it. But I do just want to make the point in this certain capabilities you might want to build yourself or look for in the tool that you adopt. And the first one is that here we can just write plain Python and get the powers of Kubernetes. And so the few things that you have to do with Flight is define an image that you're running on over here. And so these are all the dependencies, and the task environment, which is where all of the your workloads, your functions will run. And then from there, you decorate a bunch of functions. You can this is a pretty common syntax these days. And you can implement tools or just functions. So these are the tools that you saw in the previous slide. And you can compose agents, again, just with Python. So this integrates with the OpenAI agent toolkit and many other agent frameworks. And you just plop it inside a function, and you get full containerization, productionized workloads, resource requests for when you have GPU and different needs, GPU and CPU needs. So we'll get to that a little bit later. The first part of our strategy, if you recall, is to identify key leverage points in the system. You're asking the question, which LLM calls involve the simplest, most structured tasks? So you can think of this as just like structuring a text blob into JSON, that sort of thing, right? So in our case, all our downstream LLM calls here on the right-hand side are different from the orchestrator, agent orchestrator LM node on the left, right? The input and semantic space of each of these LLM calls, it's much smaller and more constrained than the agent orchestrator. And so you might do this kind of analysis, right? This is hand wavy. Don't take this too seriously, but this is my own take on each of these nodes in the agent workflow, where you start from creating the SQL CLI commands to get the table metadata, to finalizing the answer, and you kind of reason about the input space, the output space. You hypothesize about how complicated would it be, like what is the complexity level of this particular task, right? And you might grade it in terms of fire emojis. So you can see here, maybe it's the best to start with the first node here, right? So swap the LLM for an SLM right at this point, and then slowly work your way down. So once you have a good handle on that, it's now time to basically bootstrap AI unit tests. What do I mean by this? So just like you have unit tests for your software, AI unit tests are unit tests for the AI system at various levels of granularity. It could be the system as a whole, it can be specific parts of the system. But as an example, for the SQL agent, you might have your SQL data warehouse, and you may have in the logs historical SQL queries, right, that actual users have sent to that as queries, to your database as queries. So here now you want to reverse engineer like a data set that you can use to say, okay, here's my ground truth, quote unquote, even though it's synthetic data. And once you've shipped your system and you actually have user data, then you get your actual golden data set. But this is a good start, where you would, from the queries, you'd extract the SQL table schemas involved. You would create synthetic user queries. So you would say, here, given this SQL query, what is the user query that would have been asked by a human being in natural language to then be answered by this query? You would run those historical queries again and get the final answers. And in the end, you have an eval data set that you can run against your current latest version of your agent. And there's a lot of different techniques and measures that I'm not going to get to in this talk, but you have traditional NLP metrics like Blue Score and things like this, and more LLM as judge-based evaluation techniques. And you would then get a baseline for your agent's performance, assuming all of it is LLMs, large language models. So you would basically use the same platform, the same tool, to write your own agents as well as create your own ETL pipeline. So what we're looking at here is just some pseudocode for this data synthesis pipeline to create your eval data set. And wouldn't it be nice if you didn't have to adopt another tool? Next, you would optimize your experimentation speed. So this is kind of like the process you would adopt to quickly figure out whether changes to a prompt, or what is the best prompt, or what is the best model, what would that be in your system? So in this case, we're doing prompt optimization. We have a seed prompt that then you feed into an LLM to say, hey, give me some other candidate prompts that would do better at this particular task. You get some N prompts back that you run the eval pipeline on, given the eval data set. And similar to hyperparameter optimization for the ML engineers out there, it's like the best prompt using this technique. And it's super easy to do this. Just a quick note on, it would be very useful to have a way to cache results here, right? So if you have some bug or some failure in one of the nodes in this, it'd be nice to have cached all the previous evaluations of this task so that you're not wasting resources, right? So the way you would do this in flight 2 is you use this env.task decorator. You'd say cache equals auto or eval pipeline. And then you can very easily do a fan-out job for all the different prompts that the LLM came up with, just using a for loop. So again, this is just Python. You would do the same thing for fine-tuning your pipeline. So this is when you're ready to actually update the weights of your model This is probably not the first thing I would do. I would probably do prompt optimization first and then reach for fine-tuning later. Then managing costs. So wouldn't it be nice if you didn't have to use like the largest, highest common machine that you would need to host the largest model in your agent, right? It'd be great if you could use a big GPU for that one and then smaller GPUs for the other smaller workloads. So you kind of decompose your pipeline into various containers, right? That then use specific resources for that one node in the pipeline. So in this case, you can see we're using 3 different language models, Plan 3, 32 billion, 4 billion, and 8 billion. And they're all using different GPU types, which Flight enables, right? So you can create a task environment with resource requests that fit exactly the models that you're hosting in the system. And finally, optimizing inference speed. This is getting the most juice out of the system, the most throughput, so that you can deliver a really good user experience. And so here, what you would really like is a way for you to reuse the containers that you're spinning up so that you don't have to keep paying that cost of spinning up the container and loading the model into it on every agent call. So it'd be nice to have different sort of reusable container environments on which to just send jobs, right? And again, this is actually only available in Union, which is the commercial version of Flight that we're selling. But the idea remains that you would want some kind of reuse policy, in this case, that allows you to auto-scale your cluster, your like little mini cluster, as traffic is increasing, and keep those machines around to send jobs to so that you are maximally utilizing that hardware. And once there's a like 20-minute idle time, according to this example, everything will scale down to 0. And so you're not, back to the cost point, you're not using wasting idle GPU time. So that's about the end of my talk. Hopefully I have a little bit more time to address questions, but just wanted to resurface this fairly old paper here about hidden technical debt in machine learning systems. The point of this original paper is that the ML code, you see that in the black box there in the center, just a small part of the overall machine learning system that supports it, right? And I guess my argument, or my thing I'd like you to take away from this talk is that agents are kind of no different. Like the agent code is somewhat trivial in many cases compared to the infrastructure and the tooling around it that supports it in production. So, conclusion, on paper, SLMs look awesome. They look like you should be able to save a lot of money. However, this does not come for free. So you need to invest in the right tools, infrastructure, practices to really use them effectively. And here we talked about this overall strategy of first identifying key leverage points, maintaining performance, optimizing experimentation speed, managing costs, and optimizing inference speed. And we learned about how resource-aware orchestrators that are AI native can help you build these heterogeneous compute workflows for the end-to-end agent lifecycle. So not just at inference time, what the agent is doing specifically, but all the data sets and models that go into supporting it. And with that, I want to thank you for your time and attention. You can learn about Flight 2 at booth 23 here at MLOps. Unfortunately, as you can see, I'm not currently in Austin. So unfortunately, we would have loved to be there. But my colleague, Chris Madison, is there, as well as Travis McKinney. You can chat with them, learn more about Flight and just how we think about agent ops and more broadly AI and MLOps in general. So question here, are you running SLMs locally on user's machine? It's a good question. So SLMs are by design, by definition in the beginning, as you saw. They can fit on a machine, like a laptop or a desktop. I'm wondering if the question here. So yeah, no. So the system that I've kind of been talking about here in this talk is the SLMs would still be hosted on some cloud infrastructure for you to serve your users and your agent use case. So that still holds true. If you're going total indie AI user, then you would have a whole setup where you can use tools like Ollama to host the SLM locally, and run some kind of agent application just purely locally. But yes, good question about the biggest roadblock to adoption of SLM. I mean, really, it's just the additional operational burden. Like, if you're a startup in the AI space and you're not in what I'll call highly regulated industry, and this is most, I think, startups, you will start off with SaaS hosted LLMs and just using APIs. And I think that's like the best way to go, right? You don't have to manage the headache of deploying and maintaining these things. And so that's why I kind of scoped my talk to teams who couldn't do that. So teams who just by reasons of regulation and data privacy and whatnot cannot use OpenAI or Claude endpoints. SLMs. With SLMs, are we going back to the days prior to GenAI when we used to build, deploy, et cetera? Exactly. Yeah, that's precisely it. I mean, it's kind of a stack that builds on top of each other, right? So the whole GenAI hype cycle was built on this idea that, hey, you don't have to worry about the software stack below this endpoint interface, right? Just send in your tokens and you get tokens out and you can build your company on top of that. And that's still the case, right? But as I said earlier, there are many organizations, large organizations, they tend to be, who cannot rely on these APIs. And so they have to adopt the whole kind of MLOps stack to support them. Do you see any blockers for hosting SLMs completely local? Not at all, actually. So my hobby stuff is to do this just completely locally and see how far you can get. So I'm planning to get a little bit more meaty hardware, like the Mac Studios with a whole bunch of unified memory. So you can just like host a DeepSeek model, just completely the largest DeepSeek model you can just host, and you'll just pay for electricity, I guess. In terms of blockers, I haven't thought about that. It's too much. It's a good question. The tooling is pretty great. I mean, so if you know how to use a command line terminal and follow some docs and README, like you can get pretty far using the existing tooling, or hooking up a local LLM, even model endpoint, to whatever local UI that you're using to, like, I don't know, organize your documents or write a blog post or something.